Okay, so this is part 3 of the exponential functions lesson, and in this particular lesson, in part 3, we're going to talk about the natural exponential function. Now, before we do that, let's talk about an irrational number that you learned in high school geometry. So, one of the irrational numbers that you learned about was the number pi. All right, remember, pi is approximately equal to 3.14. But pi itself is an irrational number. We just approximate it as 3.14. But remember how pi came about. So basically, if you take any circle, regardless of the size of the circle, the circumference, and you look at the circumference, remember the circumference is the distance around the circle. And you take that circumference, that distance around the circle, and you divide it by its radius. Regardless of the size of the circle, divided by its radius, it turns out that the circumference, the distance around the circle, divided by its radius, for all circles, for all size circles, is equal to pi. And so it's approximately equal to 3.14. So if you take a circle, look at the distance around it, divided by its radius, it's always going to be about 3.14. Okay? Now, with regards to this natural exponential function, that number, another irrational number that you're going to learn about, irrational number, is the number e. Okay? So let's discuss how e came about. Well, basically, Bernoulli, B-E-R-N-O-U-L-L-I. So he was looking at compound interest. So he's looking at compound interest, and we're going to look at compound interest in the next lesson. And in particular, he was looking at continuous compound interest. Continuous compound interest. And he used this expression, 1 plus 1 over n raised to n power, to examine or to find what this continuous compound interest equals, so to speak. So basically, he took this expression, and it's in one of your handouts right here on page 2 of your handout. So he took this expression, and he looked at values of n that got bigger and bigger and bigger. So when n was 1, if you take 1, plug it back in, notice n is 1, so you get 1 plus 1 over 1 is 2. 1 over 1 is 1, 1 plus 1 is 2, 2 raised to the first power is 2. So notice where this comes from. If you plug in 2, you get 1 plus 1 half, and when you raise that to the second power, you get 2.25. If n is 5, you get 1 plus 1 over 5. Take that expression, raise it to the fifth power, you get this, and so on. What you want to notice, though, is n gets bigger and bigger and bigger. 10,000, 100,000, 1 million, 1 billion, and so on. Notice the values of this expression. It starts to level off. You see where it says 2.718, 2.718, 2.718, 2.718? It starts to level off. Okay, so it's getting closer and closer to some value. So if you kept on going, as n got bigger and bigger and bigger than 1 billion. And so we denote it as this, as n goes to infinity, as you get larger and larger and larger and larger, this expression gets closer and closer to some value. And we call that number e. Notice these would be an irrational number. You cannot express these numbers as a rational number. This number cannot be written as a fraction. So it's a decimal that does not terminate. There's no repetition at all. Okay, so as n gets bigger and bigger and bigger, that expression right here gets closer and closer to some irrational number that we call e. Okay, so what I want to mention here is that as n goes to infinity, this expression 1 plus 1 over n raised to n power goes to e. So it gets closer and closer to the irrational number e. But that's how and this is called the natural base, natural base, and the natural base is the irrational number e. So that's how the natural base came about. It came about from Bernoulli looking at continuous compound interest using this formula. Okay, so on your calculator, though, I want you to kind of play around with using your calculator with the irrational number e. So let's evaluate the following. Okay, number one, let's find out what e to the first power is approximately equal to. So e. So on your calculator, I'm going to go ahead and clear this. You see where it says right above the ln button? Now the ln stands for natural logarithm, and we're gonna do this in the next lesson, in a couple lessons from now. But see where it says e to the x right here, e to the x. So I want you to do is click on second, e to the x. See where you get that e raised to a power. And since I'm looking for e, and e is the exponent is to be a 1, type in 1 here, close it, and then press equal. And notice you get 2.7182812828 and so on. Okay, but we approximate this to 3 decimal places, so we say 2.718. So e is approximately equal to 2.718. Okay. Now let's figure out what e to the second power is approximately equal to. So e to the second power. So we say second e to the x, ln, so e to the x, my exponent is 2, close, press equal, and it's like 7.389, 3 decimal places, so approximately equal to 7.389. 3, let's suppose you wanted to find e to the negative 1.6, e to the negative 1.6, so let's see what that's approximately equal to. Now notice that e is a positive number, so this should still be positive. Any positive number raised to any power is going to be positive. Okay. Now remember, your base can never be, when you're talking about exponential functions, your base cannot be negative. Okay, so we get, remember we're talking exponential functions now, so e to the x. Okay, so e raised to the alright, it's e raised to the negative 1.6, close, press equal, so it's approximately equal to 2.202, so 0.202. Okay, and so for e to the square root of 3, e to the square root of 3, let's see what that's approximately equal to. So second e square root, so second square root 3, close, close. So you close the radicand, then close the exponential part, the exponent part, and press equal, and it looks like you get 5.652. 5.652. Okay, so that's how you use your calculator with e. All right, now we're going to graph a couple problems with this. Okay, so let's first of all graph y equal e to the x. It's y equal e to the x. Now, y equals e to the x, just to remind you, or just to let you know, this is called the natural exponential function. Y equals e to the x is called the natural exponential function. Okay, the natural exponential function. So remember, e is called the natural base. Okay, e is the natural base. So this is called the natural exponential function. Okay. All right. So we're going to use a t-table, and just like the previous lesson, remember the horizontal asymptote. Horizontal asymptote. All right. So y equal e to the x. Since there's no constant there, that's understood to be a 0. So your horizontal asymptote is y equal 0. So when I graph this, I'm going to get something. I'm going to do the horizontal asymptote first. So I get this. So that's your x-axis. Y equals 0 is the x-axis. And so I'm going to use the t-table. If x is 0, I get y equals e to the 0 power. And e to the 0 power is 1. So I get 0, 1. And if you don't remember that e to the 0 power is 1, many students think that that's 0, and that's not true. E to the 0 is not equal to 0. So use your calculator just to be on the safe side. So second e to the 0, close, press equal, and notice you get 1. So I'll plot the point 0, 1. So something like this. And then if I let e be 1, I get y equals e to the first power, which we know is about 2.718. Okay, we found out in the previous example. Remember, e right here is 2.718. So I get e and then about 2.718. Remember, these are approximations right here. That's an approximation. So 2.718, let's say, is about here. Oops, yeah. Oops, sorry, that's 1.718. 2.718, sorry. 2.718 is about here. In case I didn't mess this up. All right, so right here. All right, if x is, let's say, 2, I get y equals e squared. And then to find e squared, remember you just say second e to the x. So you press 2, press equal, and it's about 7.389. So 7.389. So that's about 7.4. So 7.4, let's say, is right here. And if I go with 3, it's going to be off the grid, so I'm going to stop there. And then notice, remember what we talked about, so you get this graph, which rises exponentially very rapidly. Okay? And this part goes towards the horizontal asymptote without crossing it. So there's the graph of y equals e to the x. Okay? All right, just like before, if you want to graph, let's say, y equals e to the x minus 2, let's say, do the same thing. So basically, remember what that negative 2 does is it takes this graph and it shifts it down 2 units. So your horizontal asymptote is now going to be here at y equal negative 2. It went down 2 units. Okay, so remember the horizontal asymptote. So we're graphing this. So your horizontal asymptote is going to be asymptote is going to be this number here. But remember, it's horizontal, so we name a horizontal line y equal. So it's y equal negative 2. So when I graph this, I'm going to say y equals negative 2. So here's my horizontal asymptote. All right, and then I do a t-table. If x is 0, I get y equals e to the 0 minus 2. E to the 0 is 1. 1 minus 2 is a negative 1. So I'll plot the point 0, negative 1. So 0, negative 1 is here. If x is 1, I get y equals e to the first minus 2. Use your calculator. So you're going to say second e to the first, close, just like this, and subtract 2, press equal, and you get 0.718. So it's about 0.718. So 0.718. Okay? So when I plot that, so 1.718 is about here. Now remember, it was here before. Remember that, but it's being shifted down 2 units because of that vertical shift. Okay? So remember, it was here. So 2.718, subtract 2, you get 0.718. So shifted down 2 units. Everything is shifted down 2 units. If x is 2, I get y equals e squared minus 2. So e squared. So e squared, close, then subtract 2, press equal, you get 5.389. 5.389. And it kind of makes sense. Remember, the original one was 7.389. You subtract 2, you get 5.389. So everything is shifted down 2 units. See this right here, your original graph, e to the x? So when you graph this, you're taking this graph and shifting it down 2 units. So you're taking this graph and you're shifting down 2 units. So all these points are shifted down 2 units. So this becomes this. This becomes this, and so on. This becomes this. Okay? And that's what's happening. So everything's shifted down 2 units. But this is about all you need. That's all you need. And just knowing what the graph does, what it approaches, helps to finish it off. So 2, 5.389, it's about here. And so this part of the graph looks like this. Remember, make it look like an exponential. And this part goes towards the horizontal asymptote without crossing it. And that's all it is. So this is the graph y equals to e to the x minus 2. All right. Now, if you wanted to graph, let's say this. Let's say you want to graph y equals negative e to the x. So remember what this negative does. Remember what this does. This is a reflection about the x-axis. So that's a reflection about the x-axis. Okay, so when I take y equals e to the x, and I reflect it about the x-axis, let me see if I can do a transparency here. Although I don't have my colored pens. I don't have my colored pens with me. Real quick. Nope, I don't. Okay, but notice when you take this and you reflect it about the x-axis, so basically you do a reflection like this, you're going to get this part to look like this. Okay, I'll do this. So you can see what's going to happen. So, do a t-table. If x is 0, I get y equals negative e to the 0 power. E to the 0 is 1, so this becomes negative 1. So remember, that should make sense because this point here, 0, 1, remember this graph, when I graph this, I'm reflecting about the x-axis. So that's what the negative out in front represents. So this graph, I'm reflecting about the x-axis. So 1, when I reflect about the x-axis, becomes negative 1. And that's what this is right here. 1 becomes negative 1. If x is 1, I get y equals negative e to the first. So remember, if you don't know what that is, just use your calculator. So you're going to say this now. You're going to say negative right here. So click negative and you get this. Second e to the first. Close, press equal, and you get negative 2.718. So negative 2.718. Okay? And when you start graphing that, I'm going to go ahead and graph it on this and just to show you. So I get, so the horizontal asymptote is still, notice the horizontal asymptote is still the x-axis, y equals 0. Okay, so remember that's y equals negative e to the x plus 0. Okay, so there's no constant there, so it needs to be 0. So y equals 0 or the x-axis. So it's still this right here. But when I plot these points that I'm getting, I get 0, negative 1 is here. I get 1, negative 2.718, which is here. And then I get, when I use x for 2, I get y equals negative e squared. And so on your calculator, when you do that, so negative e squared, close, press equal, you get negative 7.389. So negative 7.389, and so you get 2. So remember, for e to the x, it was a positive 7.389. For the reflection, it's going to be a negative 7.389. And so notice that part of the graph looks like this. And this part goes towards the x-axis, towards the horizontal asymptote. And so notice that this is a reflection of this. Okay, so this is y equals negative e to the x, and this was y equals e to the x. Okay? Alright, so that's going to take care of the idea of the natural base, the natural exponential function. So when you talk about the natural exponential function, you're talking about base e. Okay, base e. And base e, or the number e, is an irrational number that is approximately equal to 2.718. Okay? Alright, so that's going to take care of this lesson.